Welcome to Royal Chemistry Park, the YouTube channel. In the previous videos, we have seen what are free radicals, how they are getting generated, the stability of free radicals, and so on. In this video, we are going to see the radical reactions. I am Dr. K. Rajarajan, Associate Professor and the Head of the Department of Chemistry, Raja Sarfoji Government College, Tanjavur. Now, let's get into this video. The radical reactions may be studied under the following heads. Number 1, radical displacement. Number 2, radical addition. And number 3, free radical substitution in aromatic systems. Let's first talk about the halogenation. The reaction is best illustrated by the halogenation of alkanes, taking methane as an example. The entire process consists of initiation, propagation, and finally termination. I think you might have remember that in your lower classes you might have studied about the chlorination of methane, in which how the methane in the presence of visible or UV light, how the initiation, propagation, termination steps are taking place. He also in the initiation, first chlorine in the presence of visible or UV light, it forms two chlorine free radicals. So the formed chlorine free radical, when it reacts with methane, first it gives a methyl free radical and HCl is formed as an additional product. The formed methyl free radical, when it reacts with a molecule of chlorine, gives methyl chloride and a free radical of chlorine. And this chain will be propagated like this. And finally, when two free radicals are meeting together, then the chain will be getting terminated. This is what called as the termination reaction. So during the termination, the two free radicals, when they combine together, they will give a chlorine molecule. Likewise, when two methyl free radicals are combined together, it will give an ethane, that is C2H6. Not only like this, when different free radicals, when they are combined together, that will also give a molecule. For example, when a chlorine free radical and a methyl free radical, when they combine together, they will give methyl chloride. So in this case, the light first initiates the reaction by producing chlorine atoms. It then abstracts a hydrogen atom from methane to form an alkyl radical, which then sets the chain of photochemical halogenation. Now let's talk about the bromination by a reagent which is called as N-bromosuccinamide. N-bromosuccinamide is also a reagent which is extensively used for bromination in the laboratory. The reaction is called Old-Ziegler bromination. Although it is a specific brominating agent for allylic carbons, it is also used for aromatic and carbonyl groups. We can cite some of the examples like this, that is 1 propene. When it reacts with N-bromosuccinamide, it gives the product like this. The initiators are peroxides and less often ultraviolet light, and yields are good. When the allylic radical intermediate is unsymmetrical, a mixture of products is obtained like this. Here you can see the unsymmetrical alkene. When it reacts with N-bromosuccinamide, you will have the mixture of products. That is, two products are formed. When the double bond has two different alpha positions on either side of the double bond, substitution occurs preferentially in the secondary position. When double and triple bonds are present in the molecule, substitution occurs preferentially alpha to the triple bond. So, toluene, when it is treated with NBS and carbon tetrachloride, it gives the product like this. Allylic bromination is also possible in oximes, but these first undergo a tautomeric change, and this is then followed by bromination. All these bromination reactions are free radical reactions and may be inhibited by the presence of hydroquinone, elemental iodine, or large quantities of oxygen. Now let's see the mechanism of bromination. The mechanism of bromination by N-bromosuccinamide involves the following steps. Number one, the reaction is initiated by the bromine atom. Number two, this is the abstracts hydrogen atom from the substrate, say RH. So Br free radical plus RH giving HBr plus R free radical. This is then fast ionic reaction between N-bromosuccinamide and hydrogen bromide. Therefore, the function of N-bromosuccinamide is to generate bromine in steady state, low concentrations, and to use up the hydrogen bromide liberated in step 2 above. Finally, there is combination of bromine atoms with R regenerating the bromine and so on, so that R free radical combines with the bromine molecule giving RBr and bromine free radical. So for a long time it was held that succinimido radical abstracts hydrogen from the substrate, but this has now been proved to be wrong because the concentration of bromine is too low to permit its addition at the double bond. In polar solvents, the mechanism is different and probably there is electrophilic attack by Br plus and the abstracting species is the protonated radical. Free radical halogenation with iodine is not possible because the 71 kilocalories bond energy is lower than the energy of any carbon-hydrogen bond. Elemental fluorine reacts violently towards hydrocarbons and the reaction is too reactive to control. So, fluorinations have been studied either in gas phase or by diluting the reactants with nitrogen. Even under very mild conditions, the carbon-carbon bonds or CH bonds are broken. So now in the screen you are seeing the reactions of different process. First, we have seen the chain initiation. So in this, a methane molecule, when it reacts with fluorine, first it forms a methyl free radical and hydrogen fluoride and a generation of fluorine free radical. And regarding the chain propagation, the formed fluorine free radical, when it reacts with methane, again it forms a methyl free radical and a hydrogen fluoride. Then this methyl and fluorine reacts with methyl fluoride and fluorine free radical. Both steps are very exothermic because the hydrogen fluorine and carbon fluorine bonds are strong while the fluorine bond is weak. And regarding the chain termination, um, when two free radicals combine together, it will form a molecule. So here, when two methyl free radicals combine together, you will have a methane molecule. When a methyl and fluorine free radical combines together, a molecule of methyl fluoride is formed. Or otherwise, when two fluorine free radicals are combined together, you will have a fluorine molecule. So the elemental fluorine in presence of compounds having carbon hydrogen bonds is a good source of radical fluorine. The addition reactions of alkenes catalyzed by small amounts of peroxides are irradiated by ultraviolet light are nearly always free radical chain reactions and often lead to the formation of polymeric products. These reactions are illustrated by some examples. Addition of hydrogen bromide to olefins. This is the most famous abnormal addition to alkenes, and the entire mechanism consists of chain initiation, propagation, and finally termination. So in chain initiation, it starts with light or by thermal decomposition of initiators such as peroxides. The peroxides present in most olefin samples due to autooxidation are sufficient to initiate the chain. In fact, olefins must be carefully purified to suppress the radical processes. So here, in the reactant side, you are having dibenzoyl peroxide. When it is heated in the temperature range of 60 to 80 degrees centigrade, it forms dibenzoyl oxyradical. So the dibenzoyl oxyradical, when it combines with hydrogen bromide, it gives benzoic acid and bromine free radical. And in chain propagation with propylene, the chain propagating steps are as follows. So bromine free radical and 2-propene reacts together to give a free radical like this. And this formed free radical, when it reacts with hydrogen bromide, it gives the product like this. That is 1-bromopropane. Thus, the overall result is anti-Markovnikov of addition, that is reverse of the normal addition to the olefin. The bromine adds to the less hindered end of the bond and forms a more stable radical. Therefore, we find that with the decomposition of a single initiator molecule, a large number of molecules or the product are formed. This abnormal addition of bromine is a good method of preparing primary bromides from terminal olefins. Chain termination. Chain termination occurs by combination with bromine atoms or with alkyl radicals or by coupling or disproportionation of alkyl radicals. When two bromine free radicals combine together, it will form a bromine molecule. So, likewise here also, when two free radicals meeting together, it forms a neutral molecule here. And this is one among the disproportionation in which it will gives the neutral molecule. In presence of polar solvents or in presence of inhibitors like thiophenol or hydroquinone, the above addition becomes a heterolytic process. It is homolytic in conditions in which it is described. Homolytic addition is a result of peroxide effect and distinguishes it from ionic reactions. Now let's talk about the addition of halogens. Addition of halogens. The free radical addition of halogens to alkene although proceeding by the same steps, that is, initiation, propagation, and termination, is accompanied with many difficulties. The essential conditions are: number one, solvent should be non-polar. In polar solvents, the reaction occurs through heterolytic addition. Number two, traces of moisture or hydrogen halides should be absent even if the medium is non-polar. In presence of these, the reaction again becomes heterolytic addition. Number third, by carrying out the reaction in vapor phase, even the glass walls of the container should be coated with a non-polar inert material like paraffin. Otherwise, again, the chances of heterolytic addition increase. Number four, effect of temperatures. At high temperatures, there is homolytic substitution rather than addition. Number five, sometimes the reaction becomes reversible, and so the condition favoring the reaction in any direction must be created. The chain mechanism for halogen addition proceeds as follows. That is, in initiation, the X2, when it is exposed to photochemical equation or subject to sunlight, it will give two free radicals like this. That is, X2 giving 2x free radicals. And the propagation follows like this. They formed a free radical X. When it is added to an alkene, it forms a free radical like this. And the free radical which is formed in step 1, when it reacts with a neutral molecule like X2, it will form a neutral molecule and a free radical. So these are the things that is happening in the propagation steps. And now let's see how the termination is getting affected. The chain termination may occur in any of the ways as shown. So here you are seeing how the termination of the radicals are affected. Here you can see the two free radical molecules are combined together so that it will form an n number of molecules like this, and here the free radical character is getting lost, so that we can call this as the termination reaction. When the free radical combines with another molecule of alkene in the termination step, again a dimer may be obtained. So here this is the free radical, this is the alkene. When this free radical combined with this alkene, you will have a compound which is having a free radical. This may add to still another molecule and long chains may be built up. The process is called free radical polymerization. At temperatures below 200 degrees centigrade, addition of chlorine to carbon-carbon double bond is irreversible, but becomes reversible at higher temperatures. The rate of hydrogen abstraction increases at high temperature, and above 450 degrees centigrade, and substitution at allylic position occurs rather than addition. In contrast, addition of bromine at room temperature is often reversible. This is demonstrated by bromine radicals to olefins. Elemental iodine, when heated or irradiated, also gives cis trans isomers, showing that addition is reversible. The addition of fluorine to alkenes is a violent reaction and often give a number of products. Now let's talk about the aromatic substitutions. The aromatic compounds undergo substitution by some free radicals. The most common free radical is the aryl radical, which is generated from a number of compounds as illustrated below. So benzene diazonium chloride giving the products like this. Likewise, phenyl azo triphenyl methane gives the phenyl free radical, and triphenyl carbon free radical. So lead tetrabenzoate gives 2-phenyl free radical. The aryl radicals are generated much more clearly if N-nitroso-acetylenides are used and they yield nitrogen quantitatively when decomposed in aromatic solvents. So in this reaction you can see the formation of a phenyl radical, evolution of nitrogen and CH3CO free radical. So far in this video we have seen the radical reactions and how the process of initiation, propagation and termination effects. And we have talked about the anti-Markovnikov addition and some of the important features of the free radicals. So the remaining things we will see in the next video. Thank you very much.